Autonomous coding systems in enterprise environments run continuous, multi-file debugging loops. As these agents navigate directories and parse test outputs, their context windows expand rapidly. Sessions starting with a few thousand tokens quickly inflate to hundreds of thousands of tokens. This rapid sequence expansion carries a direct physical consequence. GPU VRAM exhausts almost immediately, and API costs skyrocket as the system struggles. The scalability of autonomous systems is currently constrained by these hardware economics and latency bounds, rather than raw model intelligence. This bottleneck is known as the inference trilemma. Under massive agentic workloads, the standard dense transformer architecture struggles to balance compute, memory, and associative recall. Look at the curve for prefill computation. As sequence length increases, processing cost shoots steeply upward quadratically. During autoregressive generation, every new token requires storing past key value activations. This creates a steeply climbing linear line representing VRAM exhaustion, hitting the red hardware ceiling. On August 11, 2026, NVIDIA released Nemotron-3.5-Lightning, a hybrid architecture designed to break these big O scaling laws. By resolving these bottlenecks, the model achieves a 52.80% score on SWE bench verified, while maintaining the operational footprint of a 3 billion parameter model. The foundation of Nemotron sequence mixing relies on Mamba-2 state-space duality layers. This is the discretized recurrence equation governing the model's memory. Instead of appending past states to an ever-growing cache, incoming tokens update a singular fixed-width latent state vector. Mathematically, this recurrence yields a constant memory complexity bound. Notice the perfectly horizontal line across the timeline. Even as token generation scales to 1 million, the memory requirement never grows. This constant memory footprint is the mandatory architectural prerequisite for running continuous agentic workflows at a 1 million token context limit. Pure state-space models exhibit a specific trade-off. Their associative recall degrades when searching for precise details over extreme context lengths. Nemotron patches this vulnerability through strategic layer interleaving. Look at this vertical stack. The uniform Mamba-2 blocks are interrupted periodically by distinct multi-head attention blocks, acting as connective bridges across the sequence. Within these specific attention layers, rotary embeddings establish direct all-to-all querying paths. This guarantees exact needle-in-a-haystack retrieval, linking the top of the context directly to the bottom. This deliberate hybridization secures the memory efficiency of linear models while maintaining the factual precision required by complex codebases. Resolving memory is only half the problem. Executing a 30 billion parameter model for every generated token drives up the computational cost per token, capping server batch sizes. To bypass this compute penalty, Nemotron replaces traditional dense feed-forward networks with a sparse mixture of experts routing system. An incoming data tensor hits a gating matrix, which draws routing lines toward a grid of distinct expert modules. A top K routing mechanism limits parameter activation. While 27 billion parameters are visually deactivated in the background, only a narrow 3 billion parameter slice remains illuminated for processing the forward pass. Notice the module block labeled shared that remains permanently illuminated. This shared expert processes every token regardless of routing decisions to enforce baseline syntactic rules and AST structures. This MoE design solves the compute paradox. The agent accesses a 30 billion parameter knowledge store, but pays the operational cost of running a 3 billion parameter model. Autonomous execution operates under strict latency limits, where step-by-step autoregressive generation is often too slow for real-time tool use. During stage 2 of the training pipeline, the architecture integrates multi-token prediction. While a base prediction node generates token T+1, multiple auxiliary nodes branch off in parallel to project tokens T+2 and T+3 simultaneously. At inference time, these integrated auxiliary heads function as a native speculative decoding engine. The engine executes a parallel verification step, where these proposed multi-token trajectories are instantly validated against high-probability paths in a single clock cycle. This mechanism results in a measurable increase in speed. The model generates tokens 1.5 to 2.2 times faster. Because native MTP utilizes the model's existing weights, it avoids the memory penalty of loading a separate draft model into VRAM. The final hardware deployment hurdle involves shrinking the physical footprint to fit within data center memory envelopes. During Stage 5 of training, the engineers applied a 4/6 NVFP4 post-training quantization protocol. This chart details the non-uniform E2M1 floating point grid. Notice how the discrete representable values, from -6 to +6, are tightly clustered near zero, unlike standard evenly spaced integer quantization. The mathematical logic is clear when you view the distribution. The non-uniform spacing naturally aligns with the actual Gaussian bell curve of neural network weights, capturing the highest density of the weight data. This static weight calibration is paired with dynamic per-tensor FP8 scaling for activations and KV caches to ensure numerical stability during matrix multiplication. This precise NVFP4 calibration proves that 4-bit compression can be deployed without losing the logical pathways required for complex software engineering. The benchmark data reveals an empirical anomaly. This 4-bit quantized model matches, and in some cases outperforms, its 16-bit baseline. This chart compares the full precision BF16 against the quantized NVFP4 model. On the SWE-bench verified coding metric, the NVFP4 model scores 52.80%, raising visibly higher than the baseline's 51.56%. On the GPQA Diamond benchmark, the model proves that graduate-level scientific reasoning is retained, scoring 75.57%. These results establish that the hybridization of MoE routing with NVFP4 calibration protects high-order reasoning from the degradation typically associated with 4-bit rounding. In modern developer harnesses, 80% of agent compute is spent on high-volume delegation, structural reconnaissance, file linting, and terminal execution. Utilizing massive, monolithic, 70 billion parameter models for these repetitive tasks incurs a high financial and latency cost. Nemotron bypasses this penalty by operating natively via hardware-accelerated tensor core instructions directly on NVIDIA Blackwell and Hopper GPUs. Nemotron-3.5-Lightning demonstrates a sustainable path for sub-agent deployment, providing frontier-level software engineering competence within an economically viable and parallelizable footprint.